Welcome to the second lecture of graph theory course. Today we will talk about matchings. A collection of independent edges in a graph is called a matching. So, let us see an example. So, consider this graph. So, here I will mark some independent edges, which means say this one, say this one. What do I mean by independent edges? So, when you consider these two edges, they do not share any endpoints. The endpoints of this edge is this and this, the endpoints of this and this. For instance, if I had selected this edge, then this will not be independent, this and this will not be independent. So, a matching is a collection of independent edges. Now, let us say see, given a matching, say this is a matching, the vertices which are touched by those edges, that means incident on those edges, are called the matched vertices with respect to that matching. And those vertices like this, for instance, which are not touched by or incident on these two edges, are called the unmatched vertices. Now, here like usual we are interested in the cardinality of the maximum matching. For instance, in this graph we can get more than this if you are looking for the independent set edges. So, this one is here, this one is here, we can in fact get this one also. This is also independent because these three are not sharing any endpoints with each other, and I can add this also, right. So, now I cannot add any more things because all the vertices are now matched. So, the biggest independent edges, collection of independent edges, that means matching, that I can get in this graph is called is of cardinality 4. And this cardinality, the cardinality of the biggest independent set of edges, biggest matching in a graph, will be denoted by alpha dash of g, and here for this graph it is 4, as we see. You can see that I have used alpha dash to denote this thing, while we had some concept which was denoted by alpha of g in the last class. It was the independence number or the stability number. What was this? This was the cardinality of the biggest independent set in a graph. What was an independent set? Independent set was a collection of vertices such that they are not touching each other, which means there is between any pair of vertices in that set, there is no edges between them. Between any pair of vertices in that set, there is no edges in between. This is similar here. We are talking about, when we are talking about matching, then they are edges, not vertices. The edges are not touching each other, that means they are not sharing any endpoints. It's a somewhat similar concept. So, to indicate that, we will use the notation alpha dash g to denote this thing. So, now let us say go back to the slides. So, here to understand what is the parameter alpha dash of g a little better, we will take some examples. For instance, let us look at a cycle. So, a cycle looks like this, as say. So, suppose let us take a simple cycle 1, 2, 3, 4. So, 6 length cycle, this is C6. So, what is the cardinality of the biggest matching here? I can mark the matching like this. So, here 1, and then once I have taken this, I cannot take this or this because then they will share the endpoints. So, I have to take this one now, and then once I have taken this thing, I cannot take this, then I have to take this thing. So, we will get alpha dash of g here is equal to 3. For instance, if we had n vertices in the cycle, suppose if I was considering the alpha dash of Cn, then it will be n by 2, as you can easily see, if n is an even number. If n is an odd number, it is not very difficult to see that this will be n by 2 floor. For instance, I can take a small example here. So for instance, I take 3 length cycle. Then once I take this edge, then I cannot take this and this. This is 3 by 2 floor. Now another example I wanted to look is the path, and similar case, the path. See path again. Suppose if you consider this an even length path, sorry, the number of vertices in the path be even. So here I have 6 vertices in the path. Then we can mark your biggest matching like this, for instance, right, 3. So this is then if then n by 2, that is Pn alpha dash of Pn is equal to n by 2 here. So that is because we had an even number of matchings, vertices in the path. Suppose it was an odd length path. So for instance, if I had taken say a 5 length path, then I cannot do this. For instance, if I take this and then I have to take this, then this will not get a partner. I will say partner. So then I will get only 2. So I will have to say alpha dash of Pn in that case is equal to n by 2 floor. Okay. So that is for the odd case. So after discussing this path and cycle of even case and odd case, we can easily see a certain property that if the number n is even, then only we can probably match every vertex. So there is only a chance of matching all the vertices is only when it is n is an even number. Otherwise, if it is an odd number, at least one vertex has to be unmatched, right. It is not that all the vertices can be matched just because n is an even number, but it is obvious that if n is an odd number, you cannot match all vertices, right. The maximum matching cannot achieve that. So for a complete graph Kn, it is clear, for instance, if n is even, then we can get a matching of cardinality n by 2, and that is the biggest possible in a graph of n vertices. Why is it so? Because each edge in the matching will touch 2 vertices. So if once we get n by 2 edges, we already have touched all the vertices, right. We cannot go more than that. Now if it is as I told, if n is an odd number, in Kn one vertices has to be unmatched, and then we will get a matching of cardinality n minus 1 by 2, the biggest one. For a complete bipartite graph Kmn, where m is less than equal to n, so what should be the biggest possible matching? It is not very difficult to see that. So if we consider a complete bipartite graph, so these are m vertices here, n vertices here, and then say so the edges are like this, between this, all the edges between this. Now of course we cannot get more than m, right. Why we cannot get more than m? Because any edge in the matching should have one endpoint here and one endpoint here. So if we have more than m edges in the matching, then here we should see more than m vertices, but it is not true. So at most m only can we get, but we can indeed get m edges, because all the possible edges are, we just have to mark 1, 2, 3 m edges here, m vertices here, and then just take this with this, say this with this, and this with this, this with this, like that. We can indeed get m edges. So for this thing, the for Kmn, the biggest matching size is equal to m. Now again, going back to the slides, so let us here is a new definition. So a matching is a perfect matching if every vertex in the graph is matched by that matching. In that case, it is easy to see that if there are n vertices in the graph, n has to be even number, otherwise as we saw already, we cannot get a perfect matching, and then n by 2 edges will be there in the matching, because if every vertex is matched, only 2 vertices can go to one edge. So, which essentially means that in a perfect matching we should have n by 2 edges. Now, that can be tell about n. So, n is an even number, and then here is a information that the perfect matching is also known as a one factor. So, it is another name which is used in the literature. This one factor, so when I say one factor, so one you may be thinking there should be a two factor also. Yes, there is a two factor, there is a notion of three factor, there is a notion of k factor in fact. What is a k factor? A k factor is a k regular spanning subgraph of G. So, there are two words coming here, regular, k regular. What do I mean by k regular? So, k regular means the degree of each vertex in the graph is k. So, for instance, we can consider say a cycle again. This is a two regular graph. That means here if you take any vertex, so this vertex, its degree is 2, there are 2 edges incident on it, the degree of this vertex is also 2, the degree of this vertex is also 2. So, every vertex has same degree 2, that is so therefore, this is a 2 regular graph, 2 regular graph. Another 2 regular graph I can draw, for instance, like this. This is a 2 regular graph together, though it is not connected, but this is also a 2 regular graph. And if I want a 3 regular graph, let us consider this graph. So, I am just putting like this, this is a 3 regular graph. So, the degree of this vertex is 3, there are 3 edges here, there are 3 edges here incident on this thing, here also 3, here also 3. So, this is a 3 regular graph. So, regular means that, and another word that we have used here is spanning subgraph. So, we already know what a subgraph is. Subgraph means we are collecting a certain number of edges and certain edges from the graph G and certain vertices from the graph G, and then putting together these things. So, making sure that the edges we select are have both the endpoints in the collected vertices. So, this is a subgraph, we had already defined it yesterday. And now suppose the subgraph, the vertex set of the subgraph is the same as the vertex set of the original graph. That means we do not lose any vertices from the original graph when we consider the subgraph. Then it is called a spanning subgraph, it spans all the vertices. So, and if it so happens that our subgraph is not only a spanning subgraph, but it is also k regular, then it is called a k factor. For instance, let us go and take an example here. So, here from this graph, for instance, if I try to take a spanning subgraph, say I can mark a spanning subgraph here, say this is a spanning subgraph. See, because it this subgraph has all the vertices of the original graph in it, but some edges are missing. So, but this subgraph here is definitely not a regular spanning subgraph. So, in this case, for instance, I could have for instance, I could have I could have considered this graph. So, I will redraw it somewhere. So, a graph like this. So, this graph, say I have modified this graph, and then in this graph, suppose I want to get a spanning subgraph and a regular spanning subgraph. So, one possibility is to collect, of course I have to collect all the vertices, but I can collect these edges. That means I will skip this edge. This is a not only a spanning subgraph, spanning because it touches all the vertices here, and then if you look at the degree of each vertex and the red, see there are two red edges here, two red edges. So this is two regular spanning subgraph of this thing, right? So like that. So when a spanning subgraph is both k regular and a subgraph is both a spanning subgraph and k regular, then it's called a k factor. So you can see that if you're talking about one factor here, then we will be selecting exactly a matching, in fact a perfect matching from the graph, right? Because every vertex should have degree only. So you here, if it select this, then this one, then we cannot select this or this or this. So therefore, otherwise the degree will go by 1. So therefore, the one factor, the word one factor is the same as that denotes the same concept as perfect matching. And now, so the more general concept is k factor. Anyway, that was just a passing remark. And then so okay, to understand this thing we can ask a question: what can we tell about a two factor? So we saw some two factors here for some graphs. So those was a cycle. For instance, that was a cycle here. For instance, this is a two factor of this graph. This is a cycle. But is it necessary that a two factor is always a cycle? So let's take another example. Consider this graph. Does this graph has a two factor? Yes. The question is, do we have a spanning subgraph of this thing which is also two regular? Yes. So this is the way we can mark it. So we mark it like this. So this one you take, then this one you take, right, and then this one you take, right. So you see that this is indeed a spanning subgraph because every vertex is included in subgraph, and then if you look at the subgraph, it's a two regular subgraph, but of course it's not connected. We don't need connectivity. So but then this is not a one cycle. In fact, it's a collection of cycles. Here we have a triangle, here we have another triangle, this is, and here we have a four cycle, right. So this is called a cycle cover because this is a collection of cycles which covers all the vertices. So this is called a cycle cover of the graph. So the another name for two factor is cycle cover. And now going back to this, in general, do we have any relation between alpha dash of g and alpha of g? We have already told this names alpha dash of g and alpha of g because of the similarity of the definitions. It's a more or less similar concept. One is about edges, one is about vertices. So we use that notation for that. But then, is there any connection between how can I relate both of them together? So here is one relation. We can see that alpha of g is always greater than or equal to the number of vertices in the graph minus 2 minus alpha dash of g. Why do I say like this? So let us explain this thing. Suppose this is a graph. I'm just abstractly I'm drawing a graph like this. This is the graph. And now if I identify the biggest matching here. So how many of them are there? Alpha dash of g of them. See this alpha dash of g, this number is alpha dash of g. So this some vertices. So there are other edges, but I'm just marking the matching which I have considered. And now what can I tell about the remaining vertices? Like yesterday also we had considered this kind of a question. What about the remaining vertices after removing these things? If I remove these 2 times alpha dash of g vertices, alpha dash of g here, alpha dash of g here, 2 times alpha dash g, what will remain? For instance, say this remaining vertices, what can you tell about? Can we have any edge here? For instance, is it possible for me to have an edge here like this? It's not possible, because suppose if there is an edge like that, then we could have added this edge also along with this collection, and we would have got a bigger matching. That means these edges and this also together would have made a matching of cardinality alpha dash of g plus 1, which will be a contradiction. We know that the biggest cardinality of a matching in the graph is alpha dash of g. So therefore this edge will never happen, never occur. So we can say that this will not be there. Okay. So now let us what we understand is, if you remove these vertices, the remaining thing what we see here is an independent set. So therefore, so this the biggest, if I am looking for the biggest independent set in the graph, the cardinality of the biggest independent set is alpha of g, and that number is going to be bigger than this number. That means that is going to be greater than or equal to n minus 2 times alpha dash of g. Okay, 2 times, okay, so n minus 2 alpha dash of g. So yesterday we had learned one connection between, one relation between this parameter and the minimum vertex cover beta of g. We saw that it was n equal to n minus beta of g, n minus beta of g. So n minus of beta g is equal to alpha of g greater than or equal to this. So now if I cancel this and then rearrange this, we will see that 2 times alpha dash of g is greater than or equal to beta of g. This is from, this is what we understood, what we studied in the last class. So what we get is beta of g is less than or equal to 2 times alpha of g, sorry, alpha dash of g. This is what we get, right, alpha dash of g. So this is what, when I rearrange this thing, when I take this thing, I take this thing here. So what I get is 2 times alpha dash of g is greater than or equal to this. But is there any relation between, actually a natural relation between this beta and this thing, so alpha dash? So we are saying that it is less than or equal to 2 times alpha dash of g, but is it possible that it is even less than alpha dash of g or bigger than alpha dash of g? Some thought will reveal that this thing beta of g has to be always greater than or equal to alpha dash of g, because if you consider any matching, for instance, let us go back to the matching here. If I want to consider a vertex cover, I have to select at least one endpoint of each of these edges. Why? Because if I do not select this edge or this edge, then this vertex or this vertex in my vertex cover, and then this edge will not be covered. I hope you remember what vertex cover was supposed to do. The vertex cover was supposed to be a set such that every edge has at least one endpoint in the in this vertex cover, right? So suppose if I do not add this and this, both of them in the vertex cover, then clearly this edge will not be covered by anyone. So it is a must that either this should go into the vertex cover or this should go into the vertex cover. So therefore the vertex cover cardinality has to be at least as much as the number of edges here, that means alpha dash of g. So that is what I have written here. So the cardinality of the vertex cover has to be at least alpha dash of g, but then not only that, it has to be at most 2 times sandwiched in between alpha dash of g and the double of it. So this is an interesting relation, and but this is for general case. It so happens that there are some situations where this is yeah, we cannot improve it much, that relation, But then if we consider only bipartite graphs, we are not interested in all the graphs but only bipartite graphs, then we can get a better result, stronger relation between these two. So it's a theorem by Konig. This theorem says if G is a bipartite graph, the cardinality of a maximum matching, that is our alpha dash of G, is equal to the cardinality of the minimum vertex cover, beta of G. So alpha dash of G is equal to beta of G is what it says. So why is it true? So if you consider, for instance, you can consider some simple bipartite graphs, you can check. So for instance, if you take, say here is a bipartite graph. So what is the cardinality of the minimum vertex cover here? Of course 2, it's a cycle. We have already seen that it's beta of G is equal to 2. What about alpha dash of G? That's also equal to 2. So similarly we can take some other examples and see. So as long as it's a bipartite graph, it's true. But you can try on a non-bipartite graph. For instance, here the triangle, its minimum vertex cover cardinality is 2. Why? Because if you want to cover all the 3 edges, you have to take 2 of them at least, right? But on the other hand, if you look for the alpha dash of G, beta of G here is 2. If you are looking for alpha dash of G, it is only 1, because you can only take one. If you once you take this thing, you cannot take this or this, right? So that's this is not a bipartite graph. So this is a theorem for bipartite graphs. Let's now see how we can prove it. The next aim is to come up with a proof for this result. So let's say, suppose Konig told us this statement, beta of G is equal to alpha dash of G. Now if we are trying to come up with a proof, so this is our approach, this is going to be our approach. We will first consider a matching, the biggest matching in the bipartite graph. Let's say it's M, and then the cardinality of M is in fact alpha dash of G. For proving the theorem, our approach will be to demonstrate a vertex cover S with the cardinality alpha dash of G. We will try to come up with a vertex cover such that its cardinality matches the cardinality of the maximum matching. And as we have already seen, this cardinality of the vertex cover can never go below alpha dash of G, the cardinality of the maximum matching. Why? Because the matching is a collection of independent edges. Each edge should have at least one of its endpoint in our vertex cover, otherwise that edge will not be covered. So definitely the cardinality of any vertex cover has to be at least alpha dash of G. Now, but it can be more than that. We have to somehow demonstrate a vertex cover of cardinality exactly equal to alpha dash of G. This is our aim. To do this thing, we will do the most straightforward thing. We will start with a matching in the bipartite graph. I will draw a figure here. So suppose I draw this, I will draw the bipartite graph like this, and then first I will mark a matching, say let this be the biggest matching here. So there are many other edges, I am just marking the matching edges. Now as we have already seen, if we are looking for a vertex cover S, then S should contain at least one endpoint of this edge, this or this. Similarly, one endpoint of this or this, at least one, this or this, maybe both, this or this, this or this. Not only that, but we are saying the Konig's theorem states the cardinality of the vertex cover is going to be exactly equal to this number, the number of the edges here, the matching, cardinality of the matching. In that case, we know that if you take this and this for an edge, then definitely we are going to have a set S whose cardinality is greater than the total number of edges here, greater than the total number of edges here, right. So, the only way is to have exactly one endpoint taken from each of these edges. Then we have a possibility of keeping the cardinality of the S set S that we are selecting equal to the cardinality of the perfect matching. But then how do we make sure that it is going to be, if I arbitrarily do that, it need not be a vertex cover. How do I make sure that we will finally end up with a vertex cover? To do this thing, we have to observe certain things. So let us say, suppose we see an edge. So there is an unmatched vertex here. There are some unmatched vertices here. There are some unmatched vertices here. Suppose this is the A side of the bipartite graph. This is the B side of the bipartite graph. So consider an edge starting from here, and suppose this edge is like this. Then clearly we are not going to select this in our vertex cover S, right, in our set. So we have to select this one in S, right, because we have to cover this edge, right. So at least this endpoint or this endpoint should be there in the vertex cover. So this one should be selected. Similarly, suppose there is an edge, if I can see an edge here like this, then since I am not going to select this one, I have to select this one. So what would be an initial approach? I will go ahead, I will search for each of these edges coming from the unmatched vertices, and the other endpoints will be selected. So one may wonder whether what happens if there is an edge like this, right, starting from here to here. Is it possible? Then which one will I select? If I select this or this, both are unmatched, then I am going to go, I am going to get a set which is more than the cardinality of the perfect matching, cardinality of the perfect matching. That is not possible, that is not allowed. So what should we do? So we cannot do anything, because we have to, since we have to cover this edge, either this or this should be there in the vertex cover. But then the good thing is that we will never have such an edge. Suppose there is such an edge in the graph, then we can argue that there is a problem, because you told that this is the biggest matching, then why don't you add this also to the biggest this matching and then make it bigger? That will be a contradiction. So therefore such an edge will never come here to here. That is why we won't have any such problems. Whenever we see an edge, only one of the endpoint will be unmatched, the other endpoint will be matched. So now the next question is, so okay, we have selected such things. Is it enough? For instance, I have selected say this thing. So I have selected this thing. So like that, whenever I saw an edge going from an unmatched vertex to this thing, I select it. Those things. See, maybe I'll consider, because I'm going to take one endpoint from each edge of the matching, then I will see which are the edges, which are the endpoints which I'm taking from this side, from the B side, and which are the endpoints I'm going to take from the remaining things I'll take from the A side. So therefore, so is it enough that I take these kind of vertices which are at the endpoint of some edge which is coming from an unmatched vertex? Of course, it is not enough, because, so for instance, you can consider an edge like this. Suppose this vertex is such that there is no edge going from this to an unmatched vertex on the A side, but there is an edge like this. And now since I have selected this, I am not supposed to select this. Then how will this edge be covered? The only way is to select this one then, right? The only way is to select this one then. So, if I have an edge starting from here and then I select this one, and suppose I go via the matching edge to the other side, and suppose I see an edge going from here and reaching another matched vertex, then that matched vertex is to be selected, because this I cannot select, because I am planning to select only one from each matching edge, each edge of the matching, one endpoint from each matching. So, it happens that whenever I see a path starting from an unmatched vertex and reaching a matched vertex, and then I follow by a matched edge to here, then again I take an non-matching, an edge from outside the matching, and then I reach on the other side, and then I follow this thing. So, then this is called, this kind of a path is called an alternating path. The definition of the alternating path, so we start from the A side, and then first it is an unmatched edge, then it is a matched edge, then it is an unmatched edge, then it is a matching edge, unmatched edge, like that. So, this kind of a path is called an alternating path. So, I can, from this thing, carefully looking, you can see that whenever I have an alternating path ending at a vertex of B, I will have to select this, because this is to be selected, then this cannot be selected, this is to be selected, this cannot be selected, and this is to be selected then. So, all the vertices of B on a matching edge, the endpoint which is an endpoint of a matching edge, and is reachable by an alternating path starting from a vertex of A, is to be selected, otherwise it is not possible. And there is another issue here. Why do we say that? I say, because I selected this vertex, I will not select this. But is it not contradictory? Because I was telling that suppose there is an edge of this sort here, suppose this is an unmatched vertex, and this is a matching vertex. So, this I am not going to select, so I will have to select this, right. So, then how can I say that I will never select this thing? So, here again, interestingly, this will never happen. Why? Suppose this happens, then I could have added this edge and this edge. So, let us say, let us use green. So, this edge and this edge instead of this edge. I can remove this edge from the matching, and I can add this and this in the matching. So, instead of 1, I have added 2. So, you have increased the cardinality of the matching, but that is not possible, because we have initially selected the biggest cardinality matching, the biggest matching. Therefore, this will never happen. But this is an interesting kind of alternating path, as you see. So, this starts with a vertex in the A side, follows an unmatched edge, then is a matching edge, then is an unmatched edge and goes to an unmatched vertex. This kind of alternating path is called an augmenting path. Why is it called an augmenting path? Because if you identify an augmenting path of this sort, you can drop the matching edges in that augmenting path, for instance this one here, and then instead of those edges we can put the other remaining edges, that means the edges from the from outside the matching. So, that will be one more than the edges from the matching. So, for instance, here one matching edge, two non-matching edge. For instance, it can be, in a more general case, it can be say for instance you can start with an unmatched edge, then it will be a matching. So, this is an alternating path, that is why this is a matching edge always, and then an unmatched edge, and then a matching edge, then maybe an unmatched edge, then there is a matching edge, and then you go back to an unmatched vertex. Now you see 1, 2, 3, 4 unmatched edges from outside the matching, and then 1, 2, 3, only 3 edges of the matching. So now instead of this, this and this, if I had put this, this and this, these 4 edges instead of 3 edges, I would have increased the cardinality of the matching, which would be a contradiction if I had selected initially maximum cardinality matching. But if you just started with some arbitrary matching, it is possible. So this kind of alternating path is called augmenting path. We have two kinds of two notions which we will later also use. Alternating path, which is essentially a path which starts from the A site and then follows an unmatched edge and then matching edge and then unmatched, matching, like that, alternates between the unmatched and matching. And augmenting path is the special kind of alternating path which starts and ends in an unmatched vertex. Therefore, as we can see, the number of edges from outside the matching will be 1 more than the number of edges in the matching edges. So therefore, you can augment by switching between the matching edges, and so we are putting those other edges in the matching and removing the edges currently in the matching, right. That is why it is called an augmenting path. Now you see these two notions, this alternating path and augmenting path. So using that, we can complete the proof we are looking for the bipartite case. The point is, you start from the A site. So our intention is to select one endpoint from each of the matching edge of the matching, each edge of the matching. But I will decide. So the end is either on the B side or on the A side. So for which all edges in the matching, I will collect from the B side is what? Here, here, here. This, how do I select that? So the rule is, I look at the alternating path that starts from some unmatched vertex of A, and if it ends in some of these vertices on the B side, then I will select that. So which are also the endpoint of the matching edges. As we have seen that we have to select that, right, by our this thing. And all the remaining edges will contribute the endpoints from the A side to our vertex cover. So the set S. Now you can easily see that this collection is going to give us a vertex cover. Why is it so? So let me group the bipartite graph vertices into these categories. So let us say these are the matching edges we considered. Now there are 3 kinds of vertices here on both sides. This is the A side, this is the B side, and here, so one category is, I will call A1. This is the unmatched vertices, and the other category is okay. The other category is the partners of the vertices from B. This is also B1, unmatched vertices here. This B2. B2 is the vertices which we selected to be added to S, right, to go to the S. Or in other words, they are the vertices which appear as the endpoint of some alternating path starts from here, and also the endpoint of some matching edge. And now remove the partners. So other than the partners, so whichever endpoints are remaining here, that is A3, and this will be also added to S. Now you can see that this and this together covers all the edges. Quickly, you can see that, as we have already mentioned, there are no edges of this sort. Now what about these edges? These edges between this and this is covered by B2. Now what about edges between, so here also there is a set B3. What about edges between this and this? There are no such edges, because so now if there is an edge, then it is an alternating path, and it will essentially, this vertex has to be here in B2. This vertex has to be in B2. Sorry, this is B3. So therefore there is no alternating path between A1 and B3. So, no edge between, so there is nothing to cover. Now, let us consider this. So, what about this kind of edges? Is it possible to have an edge like this? As we had already mentioned, so some alternating, suppose there is an edge like this, some alternating path ends here starting from here, then now following like this you will get an augmenting path. So, that is also not possible. So, these edges are not there. So, we do not have to cover anything here. And then what about this thing? This is already covered by this. And what about this thing? So, the edges between A3 and B2, they are already covered. What about the edges of this sort? They are also covered. They are also not there, because if such a thing is there, an alternating path reaches in a vertex here, and then it goes to from follows the matching edge and then goes to the B3. So, therefore, between A3 and B3 also we do not have any edge. Between A3 and B3 also we do not have any edge. Finally, we have to verify the edges which are between A2 and B3 also we do not have any edge. Finally, we have to verify the edges between, say, so this kind of edges, this kind of edges. So, what about, are we covering all of them? So, of course, these are all covered by, all these edges are covered by A3, right? All these edges are covered by A3. So, here what I have done is I have grouped the A side into 3 parts and B side into 3 parts, and based on these 3 parts I have 3 into 3, 9 category of edges in the bipartite graph. I have made sure that some categories are not possible, some edges are non-existent, and whenever they are existing, then they are covered by either B2 or A3. That is what I have argued. And now, what we have done is to get a what I have done is to show that there exists a subset of vertices whose cardinality is equal to the cardinality of the maximum matching in a bipartite graph, such that this subset is a vertex cover. So, our minimum vertex cover has to be less than equal to alpha dash of G, but then we know that no vertex cover can go below alpha dash of G. So, it has to be alpha dash of. This is what the proof of the Konig theorem. Now, the next thing is called next result is called Hall's theorem. This is in a bipartite graph, when can I say that a matching so for instance, if it is a bipartite graph with one of the parts being A and the other part being B, when can I say that there exists a matching for the A be the side, A side and B side is the 2 sides, and then when can I say that there exists a matching for this bipartite graph, in this bipartite graph which matches all the vertices of a matching of A, when is it possible? For instance, if A equal to cardinality of A and cardinality of B is equal, then it would be equivalent to a perfect matching. If a matching of A will be a perfect matching, but it need not be the case. So, the A may be smaller than B, the cardinality of A may be smaller than B. In that case, we are just looking for the cardinality of a matching which can match all the vertices of A. So, here is a result, it is called Hall's theorem, which gives a condition for the existence of such a matching. So, Hall's condition says you consider any subset of A and then you look at its neighborhood. So, what is a neighborhood? So, for instance, so let me draw the graph. Suppose this is our bipartite graph. Now, this vertex has neighbors here. See, if you look at the neighbors, these are the neighbors of it. If these are the edges going out of it, this is the neighborhood of. So, if this vertex is named U and then this is x, y, z, then we say that x comma y comma z, the set of is the set of neighbors of U. Set of neighbors of U. This is n of U. Now, we can also take a collection of vertices here, maybe U, V, W, some, and then look at the neighbor set of all these things. For instance, a vertex here which is a neighbor of at least one of them will be collected together, and this will be called the, suppose this is S, this will be n of S. N of S will be the set of vertices on this side such that it is a neighbor of at least one of the vertices from this thing. This is called n of S. Hall's condition says, suppose you consider any subset S of A, and if it so happens that the cardinality of the neighborhood of that set is greater than or equal to the cardinality of the set itself, then we say that the Hall's condition is satisfied. And Hall's theorem says if the Hall's condition is satisfied, then there will be a matching that matches every vertex of A. To checking whether Hall's condition is satisfied or not may not be very easy, because how many subsets are there for A? So, definitely 2 to the power A subsets are there, right, isn't it? 2 to the power A subsets are there. Each of them you take and consider the neighborhood and count the number of neighbors and ask whether it is bigger than the cardinality of A, the cardinality of that particular subset. This may take exponential time, but again, the condition is satisfied or not. Sometimes it is very easy to check, as we see later in an example. So, the Hall's theorem says if this Hall's condition, namely if for every subset S of A, its neighborhood n of S has cardinality at least as much as the cardinality of the set itself, S itself, then there will be a matching which matches every vertex of A. We will look at a quick proof of this. So, we will use the previous theorem, the Konig's theorem about the cardinality, so the vertex cover and matching. This is the way we do this. Suppose not, suppose the Hall's condition is true, but we do not have a matching that matches every vertex of A. In that case, so let us say there are some unmatched vertices. We will consider the biggest, we will consider the minimum vertex cover of this bipartite graph. We know that minimum vertex cover cardinality beta of G is going to be equal to the cardinality of the biggest matching. The minimum vertex cover cardinality is going to be equal to the cardinality of the maximum matching. So, since by assumption our maximum matching is smaller than the cardinality of A, that means it is not matching all the vertices of A, this thing also should be smaller than A. That means this should be less than cardinality of A. Now we identify the vertex cover, minimum vertex cover here. Suppose a little bit of it is here. So let us say x of them is here, and then how many of them are here? Here beta minus x of them are there. Now this being a vertex cover, what can I tell about the edges which are starting from a vertex outside this? How many of them are here? Here there are cardinality of A minus x vertices here outside x, because x vertices are in this vertex cover. The remaining number of vertices is A minus x, and of course this x cannot be equal to A. There should be something left, A minus x. Now all the edges starting from here has to go into this. Why? Suppose you have an edge like this, then who will cover this edge? Because this is a vertex cover, this is a vertex cover, this has to cover all the edges. If I have an edge like this, these two endpoints doesn't belong to the vertex cover, so that's not possible. So all the edges starting from the A side has to go here. So it happens that the neighborhood of this A minus x vertices outside this x, this vertices is only this much. So what do we get? By Hall's condition, beta minus x has to be greater than or equal to A minus x. Sorry, A minus x. So beta has to be greater than or equal to A, isn't it? But this is a contradiction, because beta has to be equal to alpha dash, and alpha dash we have already told is less than A. So therefore we get a contradiction. So by using, now we conclude this lecture. In this lecture what we have done is mainly two theorems about matchings in bipartite graph. One is Konig's theorem, which says the cardinality of the maximum matching is equal to the cardinality of the minimum vertex cover, and then we have shown the Hall's theorem, which says that if the Hall's condition is true, and then we will get a matching of matching which matches every vertex of A. In the next class we will consider some applications of Hall's theorem and some more ideas about matching. Thank you.